Okay, so now before we take a look at the next example, let's just kind of back up and think back to when we looked at the central limit theorem for a mean, when we looked at sampling distributions for a mean prior to the first exam. So now we're going to take x is going to denote some random variable, and let's say we know the mean and the standard deviation of that random variable. And we want to consider a sampling distribution for mean. So we're going to pick a random sample size n, calculate the mean of that sample, and then repeat over and over and over again, and then look at the distribution of what are all of the possible sample means that we could get from this population. And so what the central limit theorem for the mean told us is that, first of all, we should expect x bar to be equal to the mean of the population. Okay, so for each of our samples that we pick, we should expect the mean of that sample to be equal to the population mean. The standard error of x bar we showed was equal to the standard deviation of x over the square root of the sample size. So this makes sense that the spread of the x bars that we get is going to be related to how spread out is the population itself and how big is the sample. So the more spread out the population is, the larger we would expect the spread in our sample statistics. The larger our sample size, the smaller we would expect our distribution of sample means to be. So the standard error, the formula works out to be the standard deviation of the population, x, divided by the square root of the sample size. And kind of the last point is that we would expect this distribution to be shaped like a normal distribution. Okay, this is all true, and again, that hopefully makes some sense that we should expect most of our x bars to be in the middle, and then we are going to get some that are biased too small, some that are biased too big, and they are about equally as likely to balance each other out. And I should say that these statements are true if n is large. The larger that n becomes, the more true these statements are. When n is small, you want to be a little careful about making these generalizations. So oftentimes we have a rule that as long as n is bigger than or equal to 30, these estimates are pretty good. And I want to also, before we jump into the next problem, review one more thing. So let's consider the following example that we've taken a look at before. So let's say you're going fishing up into the mountains, and you know that on the spot that you go, on average you catch 2 fish every hour. And if you wanted to calculate how likely is it that you catch 5 fish in any 1 hour, how could we calculate that? This would be an example of what we would call a Poisson distribution. So if we let x equal the number of fish caught in an hour, and if we want to know what's the probability that x is equal to 5, well, here we would use a Poisson distribution. And for example, if we were using R, we wanted to know what's the probability of getting exactly 5 fish. Well, then we would say D plus 5, and we know that we catch on average 2 every hour. So that would be a Poisson distribution. Okay, so let's now take at the next question in the packet. And so up top here, we're just kind of summarizing the sampling distribution for mean. And so now we're repeatedly picking values of x, and let's assume that we're picking samples larger, greater than or equal to 30. This is going to be shaped like a normal distribution. It's going to have a mean, which is equal to the mean of the population x, and we've got its standard error. So let's take a look at an example which is pretty close to the Poisson distribution that we looked at. So in question 5, let's suppose that when you go fishing, you expect to catch 1 fish every 1/2 hour. Okay, so we said 2 fish every hour. Now we're just going to adjust that to say how long does it take to get one occurrence. So in this case, every 1/2 hour, we catch on average 1 fish. We could ask ourselves, well, how long is it going to take to catch 5 fish? So before we talked about how likely are you to catch 5 fish in 1 hour. That would be Poisson. If we wanted to come up with how long is it going to take to catch 5 fish, well, then we would use what's called a gamma distribution. So we haven't seen this yet. Wouldn't expect you to memorize any of these formulas. But I think what's important to note here is that we can use a gamma distribution in situations like this when we know what is the average waiting time between 2 occurrences. So here an occurrence would be you catch a fish. And so we know on average it's a 1/2 hour between those occurrences. Then we can use a gamma distribution to come up with how long is it going to take to get our successes or to get our occurrences. So in this case, let's kind of ignore these formulas over here in case you are interested about them. But let's first just kind of see how we can imagine this situation as a gamma distribution. So what we know here is this lambda, or excuse me, mu is the mean amount of time between successive occurrences. So we know that for us, our mu is 1/2. Okay, and here we're thinking about hours. So this is 1/2 of an hour. And therefore, our value for lambda would be 1 over mu, which would be 2. Okay, so basically, this is our rate parameter. So this is really saying every hour we would expect to get 2 fish. The shape parameter r in this case is, well, how many occurrences are we looking at? And here we're saying, well, how long is it going to take us to get 5 fish? So identifying these 2 parameters, the rate parameter is 2. Okay, so that's 1 over how much time on average does it take between each occurrence. And the shape parameter, that's 5 because we want to know how long is it going to take to catch 5 fish. And what's important before we take a look at a sampling distribution from this gamma distribution, we would want to note here that the mean of the population, so E of x, is equal to r over lambda. Excuse me, I wrote a mu there. So for us, r is 5, lambda is 2, so we get 2.5. Okay, so basically this is saying if we catch a fish once every 1/2 hour, how long is it going to take us to catch 5? It's going to take us a 1/2 hour for each fish on average. So altogether, it should be about 2.5 hours. And likewise, if we wanted to calculate the variance, we can use the shortcut above, which says the variance is going to equal the shape parameter, which is 5 over lambda squared. So here we would take that 2 and square it. And so our variance is 5/4 or 1.25. Okay, so let's just make sure we've got all of this straight. So x is determined by this gamma distribution, and really what x is telling us is how long does it take to catch 5 fish. And so let's imagine you go out on 30 fishing expeditions. Each time I record how long does it take me to catch 5 fish, and then I calculate the average of each of those values. So that's what x bar is represented. So we have got X bar, which is based on a random sample of 30 fishing expeditions. So what we'd like to calculate here is what's the probability that the mean time it took to catch 5 fish out of 30 expeditions, out of all of those 30 times, the mean time is bigger than 3 minutes. So here we can use the central limit theorem. So there's no requirement in the central limit theorem that says the population itself has to be normal. So even though my population is not normal, it's given by the gamma distribution, we know from the previous question what the mean and what the standard deviation of the population are. And now I could use the central limit theorem to calculate the distribution of X bar. So I know that X bar is going to be normal. I know that the mean is, I'll just denote that mu sub X bar, and the standard error, I'll denote sigma with a subscript of X bar. And what we know is that the mean of the sampling distribution, that's going to be the population mean, which we found to be 2.5. And the standard error of the sampling distribution is going to be the standard deviation of the population, which would be the square root of 1.25 divided by the square root of the sample size, square root of 30. And approximating that, that gives us a normal distribution centered at 2.5. And if I take the square root of 1.25 over 30, then that gives me approximately 0.204. So this is telling me how much variability I should expect. So most of the time, my average amount of time to catch 5 fish would be 2.5 hours, and this 0.204 is telling me how much variation in time is should I expect just due to the randomness of this process. And so if I want to know what's the probability that X bar is bigger than 3, and that, in other words, I can think of as saying this is 1 minus the probability that X bar is less than or equal to 3, for example. And if I'm using R, I could calculate this as 1 minus, and then I would use the p-norm function where X bar is 3, the mean is 2.5. And now I'm using the standard error because I'm calculating what's the probability of getting a certain sample. So I don't want to use the population. I use the standard error from the sampling distribution, which is about 0.204. And so doing this calculation, we get a value of 0.0071. So we see that this is quite unlikely that overall, on an average of 30 trips, that the mean would be over 3 hours to catch 5 fish.